Alright, let's talk about scalar multiplications of vector. So let's say we have vector b. It looks something like this. If I take 2 and multiply by vector b, what happens is the magnitude will double, but it has the same directions. So if I multiply vector b by minus 0.5, what happens is where I will have half the magnitude of vector b, but in the opposite direction. So this is half of that in opposite directions. So to sum up what I just said, the magnitude is scaled by multiplication factors. Directions is the same if multiplication is positive. As you can see here, direction is same, multiplication is positive. And opposite if the multiplication factor is negative, as you can see here. Vector subtractions. So if you have vector A going this way and vector B, which is going that way, but it's minus now, so it reverses the direction, so go this way. So the resultant is just from the tail of vector A to the head of minus vector B, and that will give you resultant vectors. To sum up what I just said earlier, negative vectors has the same magnitude but point in the opposite direction. Subtraction vectors draw the vector appropriately and continue like additions. So you draw this and then you just follow the same rule for addition. As you can see here, A minus B is the same thing as A plus or minus B. Okay. So unit vectors are, let's say, it's not too complicated. If we have a vector u, the unit vector is nothing more than just a lowercase u with a caret on top. And it has the same direction as the vector u, but it has a magnitude of only 1. Okay? So any vector u can be written in this form, where u is the magnitude and u caret is a unit vector that points in the direction of u, and has a magnitude of 1. So let's talk about 3D for unit vectors. So we have an x and y and z plane here. Z is pointing outward from the blackboard. In physics, we like to use I caret, j caret, and k caret. I caret represents direction of x, j caret represents direction of y, and k direction of z. Unit vectors parallel to the x and y, and z. So if you have I equal j equal k and that equal 1, so the unit vectors has a magnitude of 1. Let's look at vectors components. This is vector A. You can call this vector B. You can call whatever you want. So I'm going to call this vector A. And vector A can be created by a vector in the x component. Vector A can be broken up into the x component and also the y components. And we like to represent the x component, of course, we're not going to call x, we're going to use I caret. So this will be 3 I caret. And then we have 3 j caret, which is y direction. That means 3 unit to the right and then 3 unit up. So when we add these two vectors, will give us the vector A. So this vector plus that vector will give us this vector A. Any vector not lying along the x or the y axis, not lying along the x or the y axis, which is this axis can be represented by the sum of 2 vectors, this vector and that vectors. One along the x-axis and the other along the y-axis, like I explained earlier. So the 2D representations is this right here, the x component and the y component. And this right here is pretty much the same as this over here. Okay, I just put number in because we have numbers right here. So for 3D representations of vector components, you just need to broken it up into the x component, the y component, and the z component. So that's pretty much it for vector components. Let's look at vector algebra in components form. So we have to add vector A to vector B or subtract. Then we need to take the x component of A plus the x component of B, okay? And then we separate that from the y component of A and the plus y component of B. That is the y directions. And then we take the z component plus z component of A plus z component of B. Okay, so now we have this is the vectors algebra in components form. So let's say we need to multiply by a scalar, by a number. This alpha right here represents a number. Take a number multiplied by a vector right here. Then we have to do the same thing. We have to take the magnitude, we have to take the x component of this vector multiplied by alpha, the y component of this vector multiplied by alpha, any number, and the z component multiplied by the alpha. So that's it for vector algebra in components form. Let's look at 2D polar coordinates. So vector can be written as components. So you can write it in terms of x and in terms of y. Okay, we say this vector v, we can write it vx plus vy, I hat and j hat, of course. Or it can be written in the polar coordinate form. Okay, so in order to do that, we need to have a vector must have a magnitude, which represents this vector v, and a direction, so represented by this angle. So you can see here, this is vector v. So the magnitude of v, so magnitude is from here to here, it doesn't count the direction right here. This line is nothing more than vx squared plus vy squared and then square root of that. So you should remember in math class that this is similar to a squared plus b squared equals c squared. So we're trying to find c, so we just take a squared plus b squared, square root of that, and we get c. So instead of a squared, b squared, we just use vx, vy, and square root to give you the magnitude of vector v. Okay. So now that we have the magnitude, that's not enough to describe a vector. We need a direction. So to find the direction, we need to find the angle. We need to find this angle right here. And remember, angles start from this reference line, the horizontal, represent reference line here, and we go counterclockwise. Okay. So this angle right here can be described as tangent is opposite, which is vy, over adjacent, which is vx. Okay. So if you don't remember that, just review the trick a little bit. So if you want to find the angle by itself, then you just angle is equal to the tangent inverse of vy vx. You can plug that into the calculators. Okay. The other thing is, let's look over here. Let's say we are given, if we're given this quantity right here. Actually, no. We're given this quantity and we're given the angle. So how do we find vx? So we just need to say vx is v cos of angle. Okay, this cos of angle. To find the vy, we can just say v, which is this, sine of angle, that will give you vy. In the problems, if they give you this and an angle, you can use this to find vx and vy. Alright, so that's pretty much it for the 2D polar coordinates. And again, you can write two different forms, the components form, or you can use the polar coordinates. That is all for this video, and I wish you the best and see you in the next video. Peace out!